Welcome to Chapter 5, where we will be discussing acoustics. The first thing that we have to do is to start off with defining what is music. And the book defines music as the art of organizing time with sound. Now, here I've highlighted the word sound because that really is what we need to define. So, first of all, what is sound? And sound, in the big scheme of picture, is our internal interpretation of sound is subjective. It's dealing with psychoacoustics, meaning subjective, meaning that the way I perceive something, the way that I interpret something, is different from somebody else. That is referring to the psychoacoustics field of study. Now, externally, things that occur outside of the human body, something that is measurable, phenomenon that occurs outside the human body, is referred to as physical acoustics. These are things that we can measure. In this chapter, it deals with physical acoustics, not psychoacoustics. So, defining what is sound. The definition that the textbook gives is that sound is mechanical variances traveling as waves through elastic molecular medium. Now, I've highlighted certain words throughout this definition that I want to go over individually. So, what is a molecular medium? A molecular medium is a dynamical system that has the capacity to propagate a wave. This means that a medium is anything, something that we can touch or feel, meaning solid, liquid, or gases, meaning air, meaning water, meaning steel, meaning the desk, the computer. Those are molecular mediums that are something that is able to propagate a wave. Now, what is not a medium? A medium is nothing, space, outer space. A molecular vacuum, it's something that does not contain physical matter to transmit mechanical disturbances. So again, when we're talking about a molecular medium, solid, liquid, and gases, if that is removed, then sound cannot be transmitted. So watch this YouTube video of a scientific experiment of removing the molecular medium. So in this video, the scientist has a bell in a jar. The bell is going off. And now the jar is attached to a vacuum pump where it's sucking out all the air. Now, as you can hear, the bell is getting quieter and quieter. Why? Because the vacuum pump is removing the molecular medium, the air that is in the bell. Now, as he allows the molecular medium to enter back into the glass jar, the air, you can actually start to hear the bell again. And we'll stop there. Elastic. the tendency of a substance to return to its normal state after being disturbed. Gases, liquids, and solids are elastic, right? So think of a steel spring, or think of um, a tuning fork, where maybe the tuning fork, someone hits it on their knee or hits it on the side of the table, and it vibrates. It produces the noise and it vibrates, but you can actually see the tuning fork moving. But eventually the tuning fork will go back to its original state, where there's no sound coming at all from it, right? Because it's moved back to its original state after it's been disturbed. That's what we're talking to when we're referring to for molecular mediums being elastic. So the question is, can everything transmit sound? Pretty much yes. Anything that's not in outer space. Even a long ride that's 10 miles long with two people on the end, yes, that can transmit sound. So waves. A wave is a disturbance from a normal state of equilibrium that spreads through a medium. Now think about this. Think about a pool of water. When it's untouched, the surface is flat, right? And everything's spaced out evenly. However, if you were to throw a pebble in there, or to skip a pebble, you notice that it creates these waves, or these rings that come out where the water is disturbed. So think of that as sound waves actually traveling through water. So think of an equilibrium. Eventually it's going to go back to its original state of a flat surface and spaced out evenly. But when it's disturbed, it's going to create these ripples, right? It's going to create these waves that is disturbing from its normal state. Now, mechanical variances. Every physical substance is made up of vibrating molecules, right? We're all made up of atoms. The desk, the computer, the books, everything. We're all made up of molecules. Now, set at a space distance, which one is more restricted? Now, I don't, if you remember from physics class or science class, where you looked at molecules within a solid, looked at molecules within a liquid, and molecules within a gas. Within the liquids, the molecules are just sliding past each other. In the gas, the molecules are colliding and they're freely passing each other. So the least restricted environment would be gases, right? However, think about this. When we talk about speed of sound, and I'll come back to the previous slide in a second, but in an unchanging environment, the speed of sound is constant. At 70 degrees in a room, the speed of sound in air is 1130 feet per second. However, it depends on the medium it is traveling through. If you notice here, the medium of water, sound will travel at 4,756 feet per second. However, looking at steel sound will travel even faster through 16,732 feet per second. Now, going back to air, which one would it travel through faster? And the answer you should choose is steel. Steel sound travels faster. Now, it's kind of the opposite of what you may have thought, but the harder the medium, or the stiffer the medium, the faster the sound will move through it. So the desk, or a piece of steel versus air, the steel is actually going to move the sound faster through it. Now, the denser the medium, the slower the sound travels. So again, think about those two from stiffness versus density. The harder it is, the more or the faster that sound is going to move through it. Now, temperature does affect sound. Thinking of in a hotter atmosphere than 70 degrees, will sound travel faster or slower? And the answer to that is that in hotter temperatures, sound will actually travel faster because molecules are moving around faster, so will sound. So, and again, it's about 1 foot per second for every degree change. So every degree hotter, it's going to be about a foot per second. Now, when we're measuring, describing sound, everything is put into, from the physical acoustic side, is dealing with a quantification, dealing with putting a number to a physical property. So when we talk about acoustics, it's primarily a physical description, meaning it's a quantifiable number, and we'll talk about that in the next few slides. When we're describing sound waves, we are looking at frequency and amplitude, and other areas that we'll talk about in a second as well. Frequency is looking at the human perception of pitch. So humans perceive frequency as pitch. Now remember, that's not equivalent. One is more of an internal, your psychoacoustics human phenomenon, versus something that's outside the body, external, which is the frequency, which is something that we can measure. So a frequency measures the number of periodic waves that pass a given point. We'll get to more examples in a second. Now, frequency is quantifiable and is external to humans. Again, I said that earlier, that frequency is a physical acoustics, not psychoacoustics. And we measure frequency by hertz. Now, for the music majors in the class, hopefully this may make a connection with you, but when you're in the orchestra and they tell the oboe to play the A is at 440 cycles per second, or 440 hertz. Now again, I'm never going to ask you, how many hertz or cycles is a C. Only like a specialist should probably be able to know that answer. But it's just a quick little fact that hopefully you might kind of make a connection with if you are a musician. Now, taking a look at what is just a single wave cycle. Looking at the bottom of the screen here, you see the blue cycle going from the top all the way through the equilibrium to the bottom, all the way back up to the equilibrium. This is really interesting. That is one single wave cycles. Now, the two pictures that are on top of that one, that is actually 5 cycles of a wave, which actually equals 5 hertz. Coincidence. So, again, where's the beginning and start of the sound wave? So, we start measuring a single sound wave from its maximum compression, its crest, which is at the top, the highest that it goes. Then we measure to its equilibrium, which is along the average pressure line. Then we go down to its maximum rarefaction, through its trough, that's the lowest part, back up to its equilibrium. So going back, knowing that now, to the picture, you can actually count the 5 cycles that are going through each cycle, each wave going through each cycle. So as you can see here, there's 1, 2, 3, 4, and 5. All right. Now, amplitude is something different from frequency, in that amplitude measures how much energy is contained in the compression and or rarefaction of molecules that make up the sound wave. So this is, if you're trying to understand what amplitude is, we perceive amplitude as how loud something is. Basically, how loud, how soft. Now, how do we measure amplitude? And that's measured by decibels. You can actually download a decibel reader on your iPhone or smartphone if it downloads apps. They make special equipment to measure decibel readings, especially when you're referring to how loud something is. In the neonatal intensive care unit, a music therapist would go in, and maybe one of their jobs is to figure out the decibel readings of the importance of the neonatal intensive care unit. Because if something is too loud for premature babies, it's going to be damaging to them. So not only are they measuring, they're not only just going to measure the decibels of the room. However, they may use it to help the nurses and the doctors figure out better ways to care for their patients. Again, and that's only one aspect of what a music therapist can do in the room. Again, they can help with breathing, they can help with eating, again, numerous other factors. Anyway, back to the subject. But we compare sound pressure levels. The decibel scale is used. So looking at the chart, I know it's maybe a little difficult to see, but think about it. Leaves rustling in the wind is 40 decibels. And if you think about leaves rustling in the wind, that's pretty low. It's pretty soft, right? Rainfall, same thing, right? The average traffic is about 85 decibels. A chainsaw is 100 decibels. A rock concert is 110 decibels. And a jet is 130 decibels. Now, if you're ever at the airport and you're wondering why the people outside are wearing protective gear, it's mainly because of those jets. Being exposed to 130 decibels for even a short period of time is damaging. Now, here's another thing, a rock concert. If you ever left a bar or if you ever left a concert where your hearing is a little different than when you went in, maybe it's a little more muffled, or you're maybe not able to hear as clearly, it's because you're damaging your hearing. And so rock concerts, I'm a huge advocate of wearing protective sound gear when you go to rock concerts. A study recently published that vacuuming is about 80 to 90 decibels. However, listening to something at 80 to 90 decibels for about 5 to 6 hours will eventually do damaging to your hearing. Now, again, I don't think any of us will be vacuuming for 5 or 6 hours, but just think about that. For that long of exposure, it is doing damage to your hearing. Now, think about for teachers who are maybe a marching band director, or they're doing show choir, or they're inside a gym and the music is blaring. Those things, again, you have to be conscious of. Eventually, it will be damaging to our ears. Loudness refers to human perception of amplitude. All right? And we just discussed that on the previous slide. Now, waveform. Waveform refers to human perception of timbre. Waveform is a graphic representation of one complete vibration cycle. And you can look at your CD or the CD that came with the book if you have it. Again, it's not required, but it is interesting what the CD-ROM does give you. Now, think about it. Waveform and timbre. For the non-musicians of the group, timbre is the quality of sound, Think about a trumpet sounds different than a flute. A piano sounds different than a human voice. Those are different timbres. And majority of humans who do not have any type of hearing loss can distinguish between different timbres, whether it's a trumpet playing, whether it's a choir singing, whether it's a brass band, whether it's a woodwind band. You know, that's the important thing about what timbre is. It talks about the quality. Now, going back to waveform is the graphic representation over one cycle, what it looks like. Now, time, when referring to sound, is temporally based phenomena. Again, it takes time for pressure waves to travel from a source to a receiver. Now, we'll get to that in the next chapter. It's important to know that frequency, amplitude, and waveform change over time. Time uses hours, minutes, seconds, and milliseconds. However, in music, we measure by measures, beats, and parts. So, a single sound's change over a course of time is called its envelope, the sound's envelope. The change that occurs over a course of a single sound or an individual note are described as the sound's envelope. Now, again, this is usually to describe in amplitude and waveform. It's used for our human perception ears, it's used to measure how loud something is and the quality of sound. Was that a trumpet? Was that a voice? Was that piano? Now, discuss the differences between the physical and perceptual descriptions of sound. Now, we've actually gone over all of these, but I do want you to know this for the test. But for physical, when we're measuring the physical properties of sound, you have frequency, amplitude, waveform, and time. Now, physical, for frequency, we measure by hertz. Amplitude, we measure by decibels. And time, you can say that it's measured by seconds, milliseconds, minutes, hours. And waveform, you can talk about the quality of the sound, the description of the waveform itself, its envelope. Now, how we perceive the physical properties of sound, frequency, amplitude, and waveform, and time, is referred to as our perception, our psychoacoustics, our perception of pitch, loudness, timbre, and duration. And each of those match up. So frequency equals pitch, amplitude equals loudness, waveform equals timbre, and time equals duration. But please note that pitch is not the same definition as frequency, because pitch is something that we perceive as humans, and frequency is something that we can measure. That's a physical property. Now, the rest of the slides are going over a quiz that you'll have next week. So make sure you go over that before you take your quiz. All right. Email me with any questions.